right, we're going to build on the whole impulse and linear momentum thing by looking at the conservation of linear momentum, very similar to conservation of energy. That if you have what we call a truly elastic condition, your momentum will not decrease, it will stay the same. Also, we have two objects that are going to be involved in the system. The sum of their momentum, or momentums, or momenta, is going to be whatever they were at the beginning before it started. Mostly zero, but not always, as you'll see. So since we've defined momentum as E equals m times v, then the overall momentum is going to be the sum of the two different momenta that we're looking at, m1v1 and m2v2. Now, when we say linear momentum, it's going in one direction, but sometimes when you have two objects going in linear momentum, they will not go in the same direction, in which case then we get to go back to our days of vectors, as you shall see. Okay, but most of the time you're going to end up equal to zero. So let's take a look on page 217 and take a look at problem number 37. We have an astronaut that is going to be throwing a hammer forward, and he's floating around in space, so there's nothing really holding, there's no friction involved here. So when he throws a hammer, it goes 10 meters per second away from him. What is going to happen to the astronaut? Well, before he threw it, there was zero total momentum. So he's going to have 60 kilograms times the new velocity of the astronaut, plus 0.5 kilograms of mass of the hammer times the positive 2 meters per second. Now, of course, if this is going to equal zero, this has to be a negative number, which means he's going to be going backwards while that thing is going forwards from this perspective. All right? So if we take a look at this, we solve this equation right here. Well, you move, this is 5. So this becomes negative 5 rather, kilogram meters per second is equal to 60 kilograms times the velocity of the astronaut. That's the V for astronaut. We divide by 60, and we're going to get then 60 kilograms, those are the kilograms cancel out meters per second. So the astronaut velocity is going to be negative 0.0833 meters per second. So while that thing's buzzing along at 10 meters per second, he's slowly going to go backwards at less than a tenth of a meter per second. Okay? Number 39. You have a person stuck on a lake, a frictionless lake, because it's evidently rained before he got there. It's all smooth, there's no friction. Famous story about a gambler named Amarillo Slim. He's no longer with us, but he made a bet with a guy that he could drive a golf ball over a mile. The guy stupidly took him up on the bet, and he went to Wisconsin and paid a guy to let him rent a lake or a section of lake around him, and he sprayed it down with water, made it virtually frictionless, and he drove the golf ball over a mile, and I forget how many millions of dollars it was, but he won his bet. So this is kind of that scenario here. So he's sitting there, and it's kind of frictionless, so he can't move, so he takes off his shoe and throws it, knowing that the forward momentum is going to push him backwards. Clever. It takes a while, but the question here is, what is the velocity that it's going to, he's going to attain going backwards as he throws the shoe 2 meters per second away from the shore, and it also says that he is 5 meters from the shore. This is a pretty ingenious person, kind of right up there with Amarillo Slim. So anyway, so we go through the calculations here. This becomes 0.3 kilogram meters per second. Subtract it to negative 0.3 kilogram meters per second is equal to 65 kilograms times the velocity of the person. Alright, so we divide this by 65 kilograms. Again, kilograms cancel out. So velocity of the person, and I calculated this to be 1,080, well, let's see here. Actually, what I got first was, yeah, 0.00462 meters per second. It's negative because it's going backwards. So negative 0.00462 meters per second. So we want to find out how long it's going to take for them to get there. So we simply use the formula D equals VT in our physics toolbox. And then we're going to rewrite this to find, since they want to know the amount of time it's going to take, we're going to ignore that negative sign because it has absolutely nothing to do with this problem. So we're going to rewrite this in terms of T. So T equals D over V. This is 5 meters from the shore and more from the chute. And the velocity is 0.0462 meters per second. Divide that out and we get 1,080 seconds. And if you want to put that in terms of minutes, how long it's going to get to the shore, we'll take 1,080 seconds times 1 minute, 60 seconds, and it takes them 18 minutes to get to the shore. Okay? Pretty ingenious. Now, we go to this problem. This is one of those non-zero situations I was telling you about. In fact, we're going to get the overall momentum after a collision has occurred between two skaters. They're going to kind of stick to each other. I don't know. That's kind of, the problem doesn't say that, but I'm very sure after I did the calculations and saw the answer that that's exactly what happened. They collide into each other, they hang on, maybe keep from falling down, and they continue skating. One is going who has a mass of 60 kilograms, is going due east at 5 kilometers per hour. I changed that to meters per second. I got 1.39 meters per second. So his momentum is going to be 60 kilograms times 1.39 meters per second. And I did not calculate that. I just put that in the whole rigmarole there. This guy here was going south 75 kilograms. He weighed 75, or had a mass of 75 kilograms. And he was going at 7.5 meters per second, which is 50% faster than this guy was up here. And divided by 3.6 meters per second. So we multiply that by 0.208 meters per second. Excuse me. Now I know that momentum 1 plus momentum 2 is equal to the original momentum. Okay? But I got to figure out the total momentum, the overall momentum right now. So this is where the vector comes into play. So this is where my artistic abilities that are so bad are quite evident. And then I'm going to draw the corresponding vector from this point here down here. And I want to find out the resulting velocity from this. Well, so this is a vector sum. So for this, we're dealing with vectors. We're looking at a vector sum. Vector sum, that's what we did when we dealt with the velocities way back when in ancient history. So we're going to take momentum 1, which is, oh, I did do this, okay. I found this to be 80 83.4 meters per second, or kilogram meters per second. And from this one right here, the 156 meters per second. Okay? But I can't add them like 1 plus 2 is 3. This is a vector situation here. So I have to do a vector addition, which means we have to use the Pythagorean theorem. So PO, the overall momentum, is going to be the square root of 83.4. I'm not going to put that label in there. Plus, x squared by the way, plus 156. And we got to this kilograms per second here. And that's going to be squared. Take the square root of the sum of those two, and I get 177 kilogram meters per second. The question that this problem has is, what is the resulting velocity of these two intertangled skaters scrambling for their lives, trying not to fall down? So we have to take a look at the sum of the two of them together. So the overall mass is 60 kilograms plus 75 kilograms, which is 135 kilograms. The overall momentum, which is overall mass times overall velocity, is 135 kilograms times overall velocity equals to the overall momentum, which is 177 kilogram meters per second, divided by 135, and our overall velocity of the two of them intertwined, I got the 1.31 meters per second. Now, that's fine with me. If you left the problem like that, I would have no issue with that in terms of the magnitude. But if you want to go back to the original kilometers per hour, just simply multiply by 3.6, and you're going to get then 4.72 kilogram, I'm sorry, not kilogram, just kilometers per second, or kilometers per hour, that'd be fast, kilometers per second, might work. Okay, so, but we haven't fully identified the velocity, because velocity is magnitude with direction. So now we got to find the direction. Well, we notice that this is closer to the south direction. So we're going to find our theta right here. So our theta can be found by taking the inverse tangent of this value, which is this. That's 83.4. And again, the label I'm not going to worry about because it's going to cancel out. Over 156. And that angle turns out to be 28.1 degrees. And since it's less than 45, I picked the right angle. And this is this is south, and this is going east of the south. So my final answer is 4.72 kilometers per hour, 28.1 degrees east of south. And there you have it. So your practice problems here. Page 217, just do part B for number 40. Have fun.